Okay, so when we first learn physics, it's all about stuff moving in a straight line, right? But let's be real. The world is way more interesting than that. Things curve, they turn, they fly through the air. Today, we're going to get a handle on motion in all its three-dimensional glory.
So picture this. A quarterback throws a perfect spiral, or a planet gracefully orbits the sun. It's not just about how fast it's going, is it? The direction is constantly changing. Just talking about speed doesn't even begin to cover it. So how do we actually build a language to describe this kind of complex movement precisely? Well, the answer, and honestly the hero of our story today, is the acceleration vector. This is the tool that lets us tackle changes in both speed and direction at the same time. And it's what unlocks the physics of motion in multiple dimensions.
So what is this thing? Think of instantaneous acceleration like a freeze frame. It tells you exactly how an object's velocity is changing at one specific moment. And here's the really crucial part. Since velocity is both speed and direction, if you change either one of those, boom, you've got acceleration. It's a vector, which means it has its own direction. And get this, that direction can be totally different from where the object is actually moving at that instant.
And for you calculus fans out there, this is where it gets really beautiful and elegant. The acceleration vector, it's simply the derivative of the velocity vector with respect to time. It's the most direct way to measure how velocity is changing over a tiny, tiny slice of time.
This image here just perfectly captures the big idea. You see this complex-looking arrow in 3D space? Don't let it fool you. It's really just three simple one-dimensional accelerations, all added together. One for the x-axis, one for the y, and one for the z. And that idea, that simple idea, is the key to everything.
And that brings us to what I think is the most powerful trick in all of vector physics, breaking things down into their components. This is the secret weapon that makes problems that seem impossible suddenly become manageable. And here it is. This is the big takeaway, the aha moment of this whole explainer. Any complicated motion in 3 dimensions is really just 3 separate, much simpler, one-dimensional problems wearing a trench coat. It's a disguise. One for the x direction, one for y, and one for z. Seriously, this is a total game changer. Now, why does this even work? I mean, it sounds almost too good to be true, right? Well, it all comes down to this beautiful principle: independence. What happens in the x direction stays in the x direction. It has absolutely no effect on what's going on along the y-axis. This independence is our magic key. It lets us solve for each direction on its own and then just snap the pieces back together at the end.
Okay, that sounds awesome in theory, but let's see it in action. Let's get our hands dirty and walk through a real example from the source material and prove that this principle actually works. The game plan is a super straightforward 3-step recipe. We're going to start with a function that describes an object's position over time. Then we'll take the derivative once to get its velocity and a second time to find its acceleration. Simple as that.
All right, here's our starting point, the position function for a particle. You can see it's got an I component for x, a j for y, and a k for z. It looks a bit complicated, I know, describing some kind of curving path through space. Okay, step 2, let's find the velocity. All we do is take the derivative of our position function, one piece at a time. The derivative of the x component, 10t minus t squared, becomes 10 minus 2t. The derivative of 5t in the y direction is just 5, and it's the same for the z direction. So, right there is our velocity vector. Notice how the velocity in the y and z directions is constant, but it's changing in the x direction.
And for the final step, we take the derivative one more time to find the acceleration. Looking at our velocity vector, the derivative of the x component, 10 minus 2t, is simply negative 2. The derivatives of the constants, 5 and 5, are both 0. And look at that elegant result. The acceleration vector is just negative 2i. All that complex, curving motion boils down to a constant acceleration acting only in the negative x direction. How cool is that? That is the power of components in action.
Now, this component-based thinking isn't just for calculus problems. It also applies directly to a set of tools you might already know from intro physics, the kinematic equations for constant acceleration.
What you're looking at here are these standard kinematic equations. They might look pretty familiar. On the left, you've got them for the x direction, and on the right, they're the exact same equations, just for the y direction. We're not learning new formulas, we're just applying the same one-dimensional logic to each axis independently. And this is incredibly practical for real-world problems, like figuring out the motion of a skier. The process laid out here is always the same. First, you take the total acceleration, that 2.1 meters per second squared down the slope, and you break it into its x and y components.
From there, you just plug those values into the kinematic equations for each direction separately. It's a clear, powerful method to calculate exactly where that skier will be and how fast they'll be going after 10 seconds.
This quote from the source material really sums it all up. By understanding the acceleration vector and the power of components, we gain a kind of predictive power. If you know where something is and how it's moving right now, you can calculate exactly where it will be and how it will be moving at any point in the future. So the next time you see a curved path, whether it's in a video game engine simulating physics or a news report on a rocket launch, you'll know the secret. It's just 3 simple, one-dimensional problems all solved together. The only question is, what complex motion will you analyze next?